Now in this video lecture we will go through how rate of reaction depends on temperature and light. First we'll understand how the rate of reaction depends on temperature. So temperature not only increases the rate of reaction, it even helps to initiate some reactions. For example, if you take a mixture of hydrogen and oxygen at room temperature, right, or hydrogen and chlorine, I'm sorry, not hydrogen and chlorine, we'll take it afterwards. If we take a mixture of hydrogen and oxygen, the reaction is very slow, or the reaction will not occur. No matter for how many years you will keep that reaction mixture. But if the reaction mixture is ignited, then that reaction will start taking place, or that the reaction mixture will react explosively, right? And the second example we have is the reaction between carbon and oxygen. We know that carbon normally, when kept at room temperature, it doesn't react with atmospheric oxygen, right, to form carbon dioxide. But when the carbon is burnt, right, when you burn it, then that carbon will start reacting with atmospheric oxygen to give you carbon dioxide. So here temperature in both the cases, it has initiated the reaction, right? Now, so here temperature can initiate a reaction, right? Here the first was hydrogen and oxygen. When ignited, it formed H2O, right? Second example was carbon. When burnt, it forms carbon dioxide. So these are the two examples where reaction is initiated, right? Now, for any reaction, say that is taking place at room temperature, right, it has been observed experimentally that if you raise the temperature of the reaction by 10 degrees Celsius, it will double or triple the rate of reaction, right? That is, the reaction will start occurring at double or triple rate if you increase the temperature by 10 degrees Celsius, right? So we know that we measure the rate of reaction in terms of rate constant K, right? So if you take the ratio of rate constant at two temperatures that differ by 10 degrees Celsius, say I take the rate constant value at T, right, temperature T, and the second value of rate constant at temperature T plus 10, right, then the ratio of Kt plus 10 and Kt would be equal to 2 or 3, right, because we said that if you increase the reaction temperature by 10 degrees Celsius, it will double or triple the rate of reaction, right? So the ratio will come out to be 2 or 3, right? And this ratio, right, of rate constant at two temperatures that differ by 10 degrees Celsius is known as your temperature coefficient, right? So here temperature coefficient, right? I said that rate of reaction doubles, right, or triples by every 10 degree rise at room temperature, right? Rate of reaction doubles or triples when you increase the temperature by 10 degrees Celsius at room temperature, right? We know that rate of reaction is calculated in terms of rate constant K, right? So if I take the ratio of rate constant at T plus 10 and T, right, this will come out to be 2 or 3, right? And this ratio is known as, when we take the ratio of rate constant at two temperatures differing by 10 degrees Celsius, T plus 10 and T, this is known as your temperature coefficient. This is your temperature coefficient. Right, now let's understand it, right? Why the increase in temperature increases the rate of reaction? What could be the reason behind it? We have already gone through a lecture on collision theory, right? We know that as per collision theory, right, if there are two reactants A plus B, they are forming product AB, this is your product, then there are certain conditions as per collision theory, right? The reaction between A and B to form product AB will take place only if A will collide with B. That is, when both A and B will come close to one another for a collision, right? They will form product AB, right? That is, A and B collide, right, to undergo chemical reaction, right, forming product AB. Second is, these molecules that are colliding, right, that are undergoing reaction, they should also possess minimum amount of energy, right, so that they can undergo collision and form product, right? If they do not possess that minimum amount of energy, then these two molecules will simply collide and rebound. They will not form this product AB, right? So that minimum amount of energy is known as threshold energy, right? And the molecules that do not have threshold energy will not form products, right? Now there is a way, or we can go ahead and increase the energy of those molecules that do not have energy equal to threshold energy by increasing the temperature. If you increase the temperature, then energy of those molecules that have less energy than threshold energy will rise, right, or will increase to the level of threshold energy, and they will undergo collision to form products, right? Now these collisions that can form products are known as effective collisions, right? So for effective collisions, the reactant molecules should possess energy equal to your threshold energy. If the molecules do not have threshold energy, then the way to give them threshold energy is you can rise the temperature, right? So we write that reactant molecules should possess energy equal to threshold energy, right? Threshold energy to undergo effective collision to form product, right? Now those molecules that do not have threshold energy, they will simply collide and rebound. No reaction or no product will take place, right? So these are the conditions. So now let's see what temperature is doing, right? We know that if these are gas molecules and are moving randomly like this, we know that as per kinetic theory of gases, the gas molecules move randomly, right? So these reactant molecules also behave similarly, and these reactant molecules are moving randomly, right? Since they are moving, they possess energy equal to kinetic energy, because we know that every moving object, right, or anything that is moving, right, possess energy due to its state of motion, which is known as kinetic energy, right? And we know that kinetic energy is directly proportional to your temperature, right? So these moving molecules possesses kinetic energy, right? And we know that kinetic energy is directly proportional to your temperature, right? So increasing temperature will increase kinetic energy of molecules, reactant molecules, thereby increasing when these molecules will start moving with high energies, then the chances of collisions or the number of collisions will increase, that is collision frequency will increase, right? So moving molecules possess kinetic energy, and kinetic energy is directly proportional to your temperature. So increasing kinetic temperature will increase the kinetic energy, thereby increasing collision frequency, right? And we know that as per collision theory, the reaction will only takes place when a collision takes place between reactant molecules. So here increasing temperature is increasing your collisions. So increasing collision will increase your rate of reaction, right? So now we are little clear about how increasing temperature will increase the rate of reaction, right? Now there is this collision frequency which is denoted by Z, right, is directly proportional to your temperature. There is a relation between collision frequency Z which is directly proportional to square root of temperature, right? So we said here that every 10-degree rise in temperature doubles or triples the rate of reaction, right? Generally the temperatures that are selected is your 35 and 25 degrees Celsius for this. If I calculate the ratio of collision frequency at temperature 35 degrees Celsius and 25 degrees Celsius at room temperature, right, it would be 273 plus 35 upon divided by 273 plus 25. It will come out to be 308 upon this will be 298. 308 298, right? This will come out to be if you calculate this, it will come out to be 1.02 upon 1, which is 102 upon 100, right? So here collision frequency is increasing by 2, right? So if collision frequency, you just from this we have calculated that collision frequency has increased by 2, right? You can see that this is collision frequency at 35 degrees Celsius, and this ratio is originally it was 100, so it has become 102. So collision frequency has increased by 2, right? And the reaction rate we said will increase by 10 degrees Celsius. For every 10 degrees Celsius the reaction rate will become double or triple, right? So here we have calculated the collision frequency and we found that collision frequency has increased by 2, right? So this little increase in collision frequency cannot go ahead and increase the rate of reaction by twice or thrice, right? So we have to look into something else, right, that could have increased the rate of reaction to 2 times or 3 times, right? What could that be? Since I explained here, right, the concept of effective collision, right, the concept of threshold energy and effective collisions, right? So collision between molecules possessing energy equal to or greater than threshold energy are known as effective collisions, right, which I have already explained to you. So what this increase in temperature is doing is first thing is we know that the collision frequency has increased, the number of collisions have increased, but the number of collisions is not found to be proportional to the rate of reaction that has increased, right? Because this number of collisions could not double or triple the rate of reaction. So what normally happens is, if you draw a graph between kinetic energy and the number of molecules, right, it would be somewhat like this. Right, or just correct it. It will go like this, right? And let's say this shaded area. Now this representing these number of molecules, right, having this kinetic energy, right? These number of molecules, this is the maximum number of molecules that possesses energy here, this energy, and this energy is less than your threshold energy, right? So at a given temperature T degrees Celsius, some of the molecules have very low kinetic energies, right? At T degrees Celsius, this is taking place at, this graph is at T degrees Celsius. So most of the molecules have energies less than your threshold energy, right? Some of the molecules have high kinetic energy, right? You see that there are less molecules. If you look at this graph, there are less molecules. This shaded region represents energies, high energy region, right, which is equal to your threshold energy. So we have less number of molecules that have energies equal to threshold energy, and more molecules, if you find this, more molecules have less kinetic energy, they have less energy, right? So here the rate of reaction would be less. Now let's check the graph. If we increase the temperature by say 10 degrees Celsius, then there would be a drastic change in the graph, right? The graph would move more towards right. It would be somewhat like this, right? This was the original, right? This was the original graph. Now when we have increased the temperature by 10 degrees Celsius, it would somewhat look like this, right? This is how it will look like, or it's just, right, it will look like this. Now when temperature was raised to 10 degrees Celsius, you see that the number of molecules, right, that have energy, this is your, here it represents kinetic energy and here it represents number of molecules, right? So earlier this is the energy that represents your threshold energy, right? Earlier these were the number of molecules that have threshold energy equal to these are the number of molecules that had energy equal to threshold energy, right? This is the energy equal to threshold energy. Now when you raise the temperature to 10 degrees Celsius, raise the temperature by 10 degrees Celsius, you see the graph has shifted more towards right. So here now more number of molecules have energies equal to threshold energy, right? And as per collision theory, when we have more number of molecules with energy equal to threshold energy, then those number of molecules will undergo effective collisions, right? And effective collisions will increase the rate of reaction. Effective collision is when the colliding molecules possesses energy equal to threshold energy, right? So here more number of molecules have energy equal to threshold energy. So now in this case more number of molecules will undergo effective collisions to form products, right? So here basically what has happened, on increasing the temperature, more number of molecules possess energy equal to threshold energy, right? So it's not only the collision frequency, it's the threshold energy of the molecules that have increased, right? Due to more threshold energy, or due to more molecules possessing threshold energy, now effective collisions will increase, thereby increasing the rate of reaction. So increasing temperature will increase number of molecules possessing threshold energy, right? due to which number of effective collisions have increased. Effective collisions have increased, thereby increasing the rate of reaction, thereby increasing the rate of reaction, right? So now I hope this is clear to you, right? Why that 10-degree rise in temperature have increased your reaction rate, right, by twice or thrice. It's due to the threshold energy of the molecules. Now more number of molecules, you can see this, more number of molecules possess energy equal to threshold energy, right? I hope all this is clear to you. Thanks.